Okay, now it seems to work. Yeah, so apparently acuity testing is very relevant, as I understand from the lively discussion. And what you will be hearing now is actually what's behind acuity testing and many of the other tests that are done routinely to find out how well a patient sees. And it's a bit theoretical, but yeah, anyways, you know that you're doing many different psychophysical tests like acuity, visual field, also many of the color vision tests, or this is a device that measures the stray light in the eye, but also through psychophysical tests, basically it asks the patient to adjust things, to basically report what he's seeing. So it's also a psychophysical test, even though what's interesting in the end is the stray light in the eye. So these are just a few examples. And before I actually get to the topic of the talk, I just wanted to have a look at management theory for a moment, because as I said, this talk is a bit theoretical. But if you look at management theory, specifically at results-oriented leadership systems, it tells us it's not a good strategy to do things just by following detailed instructions. Yeah, it's important to acquire the core knowledge of the next higher management level to understand the respective intentions and constraints. And this then helps to act more independently at their own level and to better anticipate problems, to deal with issues that you might have, unexpected challenges, and optionally to prepare yourself also for the next higher level. And hopefully this also increases satisfaction that you have, because it helps you understanding why things are the way they are, and also it strengthens your own sense of agency, because you're basically then the one acting, not just the one executing a list of commands. Yeah, and that's what results-oriented leadership tells us. And I think that's something we can also adopt for the present case here, because yeah, this presentation will hopefully provide you with the knowledge to look at psychophysical tests from a higher level. Yeah, and that should hopefully enable you to, exactly, understand the concepts and limitations behind such tests, and allows you to use tests more flexibly and nevertheless avoid mistakes. And maybe also it enables you to design new tests or modify existing ones or use existing ones in maybe different situations where they were not made for originally, but you know what the theory is behind, so you can adopt the use to something new. So, as I said, it's a bit theoretical in parts, not everything, but I think there's something in there for everyone, and maybe there are a few things where you need to go through again to really maybe understand it. And also I've been told that at times I talk a bit too fast, so slow me down if you think that's true. Yeah, it might be true. And Dr. Morney has demonstrated that the lecture does not need to remain in time, so we can overrun, yeah. And then I simply talk slower. So this is a picture by an artist called Fritz Kahn, and that's how he depicted what happens in the brain when we see. So that's a key somewhere in the outside world, and the image of the key is projected to what seems to be the retina or something like this. Then a lot of processing takes place. There's someone sitting or standing in the brain and actually doing something, and all this then ends up in that person vocalizing something that, in that case, Schlüssel, which is the German word for key. Yeah, and even though probably not even the artist thought that this is exactly what happens in the brain. Yeah, it tells us there are many processes that need to take place in order to link what's in the outside world through the eye and everything that comes afterwards to a response. Yeah, and in psychophysics we rely on the responses of the people, and the responses depend not only on the eye but also on everything else that comes behind, until you finally hear what letter the patient believes that he has seen. Yeah, and psychophysics actually has two meanings, and one does not always clearly separate these two meanings. There's psychophysics as a scientific discipline, and it was founded by a person called Fechner, and as always in science, people build onto what has already been done, and he builds onto what Weber has done. And what he said is, to me, psychophysics is a science of the relationships between the body and the mind, which is based on the link between the physical and the mental measure. It's thus part of the exact sciences. So even though it deals with what's going on mentally and so on, which maybe is a bit difficult to understand, he nevertheless says it's an exact science. Yeah? And it links basically the body and the mind. And here the idea that the body and the mind are two distinct things, and that's of course something one could argue about, yeah. But nevertheless, as we will see later on, it can be something useful as a concept to think about things, even if you don't believe that mind and body are completely separate. He also said, I differentiate between outer and inner psychophysics depending on whether it's about the relationship of the mind to the external physical world, so what's out there, what we could see, for example, and or the internal physical world. So basically there's the internal physical world, that's basically what we would maybe call physiology, yeah, and the mind that somehow links to the physiology. And he differentiates between the two. There's basically one mind, and that there's the outside physical world and the inside physical world, which is basically physiology. But psychophysics is also a method, and that's how we very often use the word, like a method as we use it in visual acuity tests, for example. And it's basically an investigation of sensory processing based on the subjective perceptual performance as reported by the observers. So the observers, in your case, mostly the patients, have to tell you something. It's not that you're really measuring something in the sense of that you get a physiological signal. You're not measuring blood pressure maybe, or you don't measure whatever, what the minerals in the blood are, or whatever you could think of, but you are relying on what the person is telling you. And yeah, so these are the two meanings of psychophysics, and this here now, this picture illustrates once more what that Fechner guy has tried to express. So there is the stimulus, that's what's outside in the world, the person that you're looking at, or the view that you have out of the window with all these different things there. And then there's a percept. The percept is what people kind of consciously experience as what they think what's there, yeah. What there is basically the result of the vision process. And in between the two is the neuronal activity. That's what's happening. Basically from the stimulus, the stimulus kind of triggers neuronal activity that creates what we perceive. And there's also that edge of the triangle, and that edge is the outer psychophysics, the link of the stimulus to the percept. The percept is basically the mental representation of what's there, basically what Fechner called the mind, and that's the outer physical world. Yeah? And that's the neuronal activity here. That's what Fechner called the inner physical world. And that's what's happening in reality, and that's what we are usually examining when we are doing psychophysical tests. And we are trying to conclude something about this pathway here, even though we are going along this edge of the triangle. For example, we are trying to conclude that whatever, the photoreceptors don't work, or the ganglion cells don't work, or maybe the visual cortex does not work. That's all something here, yeah. And but we are not really measuring that. We are walking along this edge of the triangle with our psychophysical tests. Yeah. And if you're doing a psychophysical test, one of the most important concepts in practical psychophysics is what's called the threshold. And the threshold, the very classical threshold in psychophysics, is a threshold for detection. What Enyam has talked about is not so much detection, but rather basically the differentiation between different symbols. You might still see a blob somewhere on the chart, but you cannot differentiate what letter it is or what Landolt orientation. But this is, at this point, first what I talk about is detection. Basically whether a faint light source can be seen or not, or if that's basically flashing briefly, do you see that flash or not? And if the energy level is very low, so basically the light is at a very low level, let's see on that axis, you have a very low chance of actually seeing it. That's the probability of detecting it. Yeah? And if it's high enough, then you see it, then you always see it. That's the probability of detection of 1, which means 100%. And the naive way of what you might think what could happen is that at some point, coming here from the left, it's strong enough, and then you start seeing it. Yeah, and that's not what happens in reality. In reality, it is that there's that kind of slogan: the nature does not make jumps. Yeah, in nature, normally everything is going somehow smoothly, and there are not sudden changes usually. And this is how it usually looks like when you measure this. Again, the probability of detection, and here that energy level of the light, and you see it's going more smoothly. Even here, there's also a certain chance of detecting the light, and here you might not detect all of them if you repeat that experiment over and over. And this is basically where the steep jump was here, and you see, okay, this is probably like the turning point, the inflection point of the curve, but overall it's more smooth. And this idea of the threshold is often attributed to a person called Herbart, and he is one of the founders of mathematical psychology. And the question is now, why do we have that slope there? I mean, it's nice to say the nature doesn't make jumps, but there must be a reason for that. And the reason is that there's noise in the system. For example, the neurons in the brain, they're always doing a bit, they're always slightly active, yeah, and sometimes a bit more active, sometimes a bit less active. And if now that signal from that faint light comes in, and the brain in that moment is a bit more active, then there might be a chance that this actually activates the next stage of processing, because it basically the faint stimulus and the relatively strong random fluctuations of activity in that moment add up, so that next stage thinks, oh, there's a light. And if this random fluctuation of neural activity at that moment is relatively low, then the doesn't add up that nicely, yeah? And then the next stage of processing doesn't realize that there is a light. And as this fluctuates, sometimes it adds up, sometimes it does not add up so nicely, and therefore you get this smooth transition. And that curve, what we see here, is called the psychometric function. Basically, it describes the result of the mental processing. Yeah, here again we have a psychometric function. And what we take as a threshold if we get such a measurement is usually we look at the point where we have seen 50% of the stimuli, or the person has seen 50% of the stimuli, and then we go down here and we can read the stimulus intensity, which is considered the threshold value. And it makes sense to take this 50% point if we assume that the shape of the curve is like this, because that's the only special point. If you would go a bit further up, then we might ask, oh, why don't we go even further, or maybe even further? Or we could go a bit further down, but why not even further down? This here, the inflection point is somehow special because the curvature changes from leftwards to rightwards. And it's also the steepest point of the curve. And that's relevant because if we do an experiment where we detect light stimuli, this is actually the outcome. We present the light very often, yeah, and record how often it is seen for a given strength of light. So basically the measurement result as such is on that axis, but we want to translate it into a threshold here on that axis. And if the curve is steepest here, measurement uncertainty here on that axis, that we have, and we always have in every measurement we have a slight uncertainty, yeah, then certainty on that axis translates into a relatively small uncertainty on that axis. And if you would go to a place here on the curve where the slope is not that steep, then an uncertainty on that axis would translate into a higher uncertainty on that axis. We can do similar experiments where we don't ask, was there stimulus or not, like was there light or not, but we could ask, are two lights different or the same? Then we are asking for the presence of a difference. And this is then called, what we are looking for then is called the just noticeable difference, known by the psychophysicists as J and D. And that gives you basically the same curve. It's just a different axis label and, of course, a different result. And how could such an experiment done practically? There are classical approaches. One of them, and these classical approaches are not out of fashion, is the method of limits. That's something you might know from hearing tests. If any one of you ever has done a hearing test, very often they are done by basically cranking up the volume more and more and more until the patient says, now I can hear it. Or they come from the other side and they turn down the volume more and more and more until the patient says, I cannot hear it anymore. That's one possibility of doing such a test. There's usually a hysteresis, so depending on from which direction you come, you end up at a bit different value, but that's one possibility of doing it. Then there's a method of constant stimuli. That's basically you have a set of fixed values that you want to test, and at each value you present, for example, 50 repetitions, but only at these values that you decided for, like 20 different flash strengths, for example. And that gives you then basically something that very much looks like this. You have certain points where you measured, and then you have to fit a curve in there. There's also a method of adjustment that you try to adjust the reference stimulus to match a stimulus that is the actual interesting stimulus, depending on the type of experiment, of course. That might make sense in some cases. What's more modern are staircase procedures, because you can imagine, for example, with a constant stimuli, you have to know roughly in which range you want to measure, otherwise you cannot select your range of stimuli that you want to cover. And sometimes that's not very clear, and you would like to measure as much as possible around the threshold, because that's the most interesting part of the curve. And if you're measuring in a range where the person anyways always sees something, then it's not interesting. Or in a range where the person cannot see it anyways, then why measuring there? Yeah? You can put 10 different stimulus strength in that region down here. The patient won't see it anyways, yeah? So it's not worth trying. But you want to measure around this range, so this range of stimulus strength here. And sometimes you don't know that beforehand, so what you do is a staircase procedure where you start with a certain value and you see the result, and if the patient, for example, or the subject in an experiment detected it, then you know, okay, it was easy enough, then let's make it more difficult, let's reduce the flash strength, and okay, still detected, then you make it more difficult. At some point the person will say, I don't detect it anymore, then you make it easier, and then in the end you kind of oscillate around the threshold, because sometimes it's seen, sometimes it's not seen, so you always change the direction of how you change the values. And this is something that's represented here. In the beginning it was relatively easy, or the patient says, yes, I see it, then more difficult, yes, still yes, no, you reverse the sequence basically, and it says yes, no, yes, no, yes, no, yes, and it will continue somewhere around here, and then you know, okay, around here must be the threshold. And now here it's what's on this axis now this flash strength, what was on the x-axis here. And this is now the trial number basically. And then we have our curve that we measured, and now we can wonder if we have measured the curve several times, yeah, maybe before treatment and after treatment, or maybe you want to know how different people perform relative to each other, things like that. We want to compare different curves. Then we can wonder, okay, what does a shift of the curve imply? For example, if the whole curve keeps its shape, but it shifts rightwards or leftwards. Or we can wonder, what does a change in slope imply when it's getting steeper or like shallower? And if the blue one is the original one, let's assume, then if the curve moves to the left, then this means the person has become more sensitive. Basically, less stimulus strength is sufficient to reach the level where the person could detect it. And if it's moving to the right, then the sensitivity of the person has decreased. Yeah, so you need more flash strength for the person to say, I've seen it. And if it's shallower, then that means more noises in the system. That, for example, the brain is producing more noise, or the retina, somehow the workings of the structures in the retinas produce more noise. That would be less noise if it's deeper. This one, that's basically starting here at the same point, but going up in a shallower way, that could be fluctuating attention, that sometimes the person is attentive and really doing well, and sometimes the person simply isn't attentive and misses stimuli. And then you might get a curve like that. And the psychophysicists, they are very conscious about the words that they are using. And one word that they are using is sensation, and the other perception. And maybe in everyday life, you would not really make a big distinction between the two words, but to talk about that from a theoretical perspective, it makes sense to know what they are supposed to mean. And sensation, the word sensation is used for the sensory organs taking up energy from the environment and transforming them into neuronal signals. So basically the step from the stimulus to a neuronal signal, that's sensation. And the processing that takes the initial neuronal signals and somehow processes them more and more and more until you know what you have seen, that it's a car or your grandmother or whoever. Yeah? That would be called perception. And that's two different steps that are often considered as one thing. But if you want to think about it from a theoretical perspective, it's good to differentiate between them. And before we get deeper into the theory, I want to quickly mention the Weber-Fechner law, or sometimes it's just the Weber law. And probably some of you know that law because it basically explains why, for example, an acuity chart is scaled the way it is with the different sizes on it. But it's not just for acuity, and a very practical example is if you, sorry, no, that was the wrong button. If you take a case of German beer, yeah, it's the beer itself, it comes in glass bottles and the plastic case around it, and that's pretty heavy. And now you put on top of it very tasty Ghanaian chocolate, yeah, and you're already carrying that case of beer. You won't feel that someone put on that bar of chocolate, yeah. The difference is simply too faint to feel it. But if someone would put a second case of beer on top of it, you would for sure feel it. Yeah, it would be much heavier. And if you would start with a bar of chocolate, yeah, and you put on a second one, you would probably also feel it, yeah, because you start with a relatively low weight, and then you would feel that another relatively low weight would be added, yeah. So in this case, you feel the chocolate in this, no, you don't feel the chocolate in this case, you feel the second chocolate in this case, which means it's not about the weight per se, but it's about what you already carry. And that's an important part of the Weber-Fechner law, basically important for feeling that something has changed is also not just what you're adding, but also the base amount that you already have. And that's the same for vision. That, for example, if you have well, the animation is not completely proper now, there's something missing, or it's not showing. I think the projector is not reproducing the gray levels as it should. So here's a very faint Landau C. Yeah? It's maybe not visible, at least to me. I can only guess that it's there, but it's there. Yeah? It's a very faint Landau C. The projector doesn't like it. If you add that faint Landau C to an already existing strong Landau C, both on top of each other, you get this Landau C, but there's hardly any difference between the two. Yeah? If you add to this one, a similar one, then you see it's getting darker, so you can kind of see that there's a difference between the two, even though the projector still doesn't like to show it really. And here, if you take a faint Landau C and take another faint Landau C, if you add the two, then you will see that this one is much stronger than this one. Yeah. So you probably can guess what should be there. So, that law does not apply only to carrying cases of beer, it also applies to seeing. For example, when you're looking at contrast level, and it also applies to acuity charts where the steps between the lines are not simply always the same centimeters or same visual angle between one line of the other, but it's rather a multiplication, a certain factor between one line and the next one. And yeah, Fechner phrased it like this: the increase of the tiny wealth of a poor soul by 1 thaler. Thaler is a currency unit. So the increase of the tiny wealth of a poor soul by 1 thaler is easily recognized. the same numerical or objective increase of the wealth of a millionaire is below of what could be recognized. It seems that we have to differentiate between value and value. Accordingly, Laplace, a different scientist, has proposed the valeur relative. And yeah, this picture again shows what I've already explained to you. And one can, of course, shape that into an equation, which means that the ratio between the difference and the base value is a constant. So you always need to add something proportionally to so that you can start feeling it. And this is what's known as Weber's law. And as you can see here, and it's always the case in everything, there are limits to these laws. Yeah, and if you go to very low weights, then you see that this Weber constant, this delta R divided by R, is not constant anymore. These two curves represent two different people. You have basically the base amount, the base weight here, and here you have the constant, which gives you how much you need to add proportionally so that you can start feeling the difference. And this proportionality constant is roughly horizontal here, so it remains equal until you get to very low weights, just below the weight of a candy bar or chocolate bar. And then this Weber, I don't want to go through all the details, but Weber has then transformed this into another equation. And but the important part here is that he related this delta R divided by R to a value that's that he called delta E. And he said this is the just noticeable difference in sensation. So he says, okay, the stimulus produces a sensation, basically the initial neuronal activity, and the next stage needs to detect this change in neuronal activity. And this here is the smallest amount of change in neuronal activity that the next stage can detect. And for him, that was extremely important because in his view, this this created a link between sensation and perception. So he believed that he had discovered the fundamental principle of body and mind interaction through this mathematical equation. I don't know why. Okay, yeah, no, that's unhidden. Yeah, that's just what I want to mention. He believed that he has resolved the riddle of how body and mind are linked in this equation. And the psychophysicists, the basically hardcore psychophysicists, they meet each year on the 22nd of October and have a little conference somewhere, because this idea that Weber had, and this idea he got in the morning while he was still laying in bed on the 22nd of October. Yeah, so this is kind of the celebration day for the psychophysicists. And if we go one step further, now we had seen that concept, or this abstract concept of inner psychophysics, outer psychophysics, and so on. We had discussed how we can do measurements, at least detection measurements, and we had this Weber law and so on. And we can get one step further, and for that we need signal detection theory. And this is something that describes how an observer perceives a stimulus. On a theoretical level, it describes it. And so it describes or it provides a description that relates to questions like, is there something out there? Or what is it, what we see? And because psychophysics is based on the perception of the subject's perception, signal detection theory can also be used to describe psychophysics. And the origins of signal detection theory actually are in World War II. World War II also affected a bit Sub-Saharan Africa, I guess, but like a major site of fighting and destruction and so on was in Europe. And the Germans at that time were not the good guys, yeah, and they sent bombers to London, for example. And then there was a question in London, are bombers coming? So that, and if they would know that bombers were coming, they could hide in shelters. Otherwise, they could try to follow their life as normal, that they would normally, and do whatever they needed to do. And of course, they didn't want to seek shelter every half hour or so, yeah, because that would disrupt life completely. But they, of course, wouldn't want to miss any real bomber coming and dropping bombs, yeah. And that were the early days of radar. And this is basically a radar image that the people might have seen on their radar screen. And there are different things. There's ground clutter, reflections by things on the ground. The weather, like heavy rain, can cause signals on the radar screen. This might be a flock of birds, or maybe not. And these are targets, these are probably bombers. And it's hard to differentiate them from other stuff going on, maybe from that flock of birds, or from certain types of ground clutter, or maybe small spots of heavy rain or something, yeah. So it was a challenging task for the radar observers to judge what's there and then to decide, okay, this is probably a bomber, I have to tell the people to seek shelter, or it's nothing dangerous, simply go on with your life, yeah. And if they would tell them too often that they should seek shelter, then at some point they wouldn't listen to them anymore, yeah. And that would also not be good. So this is basically the origin of signal detection theory. And we can have a look at a different practical example. There's that little boy laying in his bed. And as you know, children are afraid of the dark. And in the dark, maybe there are strange noises that appear coming from a monster, maybe, that hides under the bed. Yeah, could be. The question is it really a monster? And if so, my mom has to come and save me. That's what the child thinks. Yeah. So the question is, should the child call mom or not? And there are different possible outcomes. Yeah. If he calls his mom and the monster really exists, then mom will of course save him, yeah, because mom is almighty and can fight the monster. If he doesn't call the monster in that case, yeah, doesn't call the mom, then he might be eaten up by the monster. That's not the preferred solution, yeah. If he calls his mom, but the monster doesn't exist, then mom might be angry. That's also not the best solution. Maybe slightly better than being eaten. Yeah. If he doesn't call mom and there's no monster, then he simply can continue to sleep. That's basically the perfect solution. So, all in all, this and this are good solutions, and this are not so good solutions. And there might be response biases, of course. Yeah. If the child has to choose between making his mother angry or being eaten, then possibly he has a preference of the mom being angry rather than being eaten. And yeah, the preference depends on cost and benefit, and it's clear in that case what are the costs and benefits. Maybe it depends a bit on the character of the mother, but generally it's clear. And yeah, that illustrates it. I think I've already said that. So in doubt, the child probably thinks, if I'm in doubt, I should rather call my mother. And that's of course something that does not only happen for children when they're in bed at night, but also in other situations. If you're walking, I don't know, through some grasslands, and you see something weird through the grass, and you don't know what it is. The question is, should you run away, or maybe just continue whatever you want to do? Yeah, and I mean, you have to do certain things that day. Yeah, I mean, you need to maybe get somewhere to get some food, or you need to get some water, or meet a friend or something, and you don't want to cancel all these things and run away. Yeah, so if you don't want to run away because that's just a faint hint of something hiding in the grass. Yeah, but of course, if it's a real tiger or something, then you want for sure run away, or I don't know whether it's strategically good to run away, but at least do something useful. Yeah. So it's a real life problem for everyone, essentially, not just for these children. And an important factor in here is the decision criterion. The decision criterion is from which signal strength, and in this case of the child, from which monsterness on that the sound has, should I assume that the monster is present. And at some, basically at some cutoff value of that monsterness range, the child will say, okay, this sounds too much like a monster and I will call my mother. But that's something that the child has to decide. That's not something that the monster decides, that's the child that decides it. And if the child decides for a large value, then few monsters will be detected, because it then it really has to sound like an extreme monster so that the child says, okay, this is a monster. But there are also few false alarms, because with that strategy he will catch almost all the monsters that there might be. Yeah? Even the small ones that maybe don't make such a big monsterness sound. If we choose the small values, just oh no, I was one ahead. There will be few false alarms, meaning he won't catch the small monsters, basically. Yeah, I've confused the 2 points already. But there will also be few false alarms that whatever makes sound that remotely sounds like a monster, he will for sure not call his mom. That's the point here. Sorry. But if you get to the small values now, there will be more monsters detected. Also, the very small monsters that just make a faint monsterness noise, they will be detected. But there will also be more false alarms. Like there might be other things that sound a bit like a monster. And well, he won't call his mom for that then. If he will call his mom for that as well. Sorry, my mind is already a few steps ahead. So, well, I think it's become clear that there's a decision criterion that will decide whether there are few false alarms and a lot of false alarms and vice versa. So, if we do that on a more abstract level, or we generalize it basically beyond monsters, you could come up with this table. It's essentially the same table that we had before, and we are now in the vision domain. So there could be a response: yes, I see it, or no, I don't see it, and the stimulus could be present or it could be absent. And these are the correct combinations. There's so-called hit and the correct rejection, and here there's misses. These are misses should be avoided, and the false alarms should also be avoided. And now this brings us to signal detection theory. Finally, I'm sure you all have been waiting for that. And the responses, whether the stimulus is perceived or not, always depends on 2 factors. One is what's called the sensitivity, D prime, and I will explain to you what that is. And the other is the observer's decision criterion that we have already mentioned, That's something that the observer is free to choose, basically. And now we will assume that there's no a priori knowledge about signal probability, so we have no idea whether there are monsters or not. Yeah. Otherwise, of course, we would have a bias in how we decide. The mother, for example, knows that there are no monsters under the bed, so she will always decide against monsters. But in that theoretical discussion now, we will first assume that we don't know anything. So we could describe the situation like this. That there could be what's called the noise-only situation, which gives you a certain strength of sensation. In that example, the strength of monsterness. And the probability that we get the strength of sensation. And don't be confused that here some curves are going below zero. That's basically an arbitrary 0 point here. It must be placed somewhere. It makes sense to place it here because this hill here, which looks like a Gaussian curve, that represents basically the case that there is no signal present, and its highest point is therefore is placed at 0, which kind of makes sense, but it's kind of arbitrary. And the noise, of course, means that sometimes, if you measure that signal, sometimes you will be the noise will be unusually low. Then you will get to the left side here, and the more to get to the left side, the more unlikely it is that you get such a value. And the noise might also be a bit higher in a specific case of measurement, so you are on that curve. So we have on that side of the curve. And the noise is unlikely to be extremely high, therefore that curve goes down here and reaches almost 0 here. So that's a basic Gaussian curve with a highest point where the signals, where basically around no signal, yeah, which therefore that 0 was chosen here. But if you have a signal present, then the whole curve shifts to the right, because now we have a signal, but the noise is still present in this, like the neuronal noise in your brain, yeah, for example, or what noise in the photoreceptors, all these things, they are still present. So now comes on top of that noise the signal, yeah, but the noise is still there. Therefore, you still have that hill here, but it's shifted towards a higher value because the noise and the signal has been added. And these curves have an overlap. So if you're sitting somewhere here and you're measuring a specific value, you don't know whether the value belongs to this curve or whether it belongs to this curve. And that's basically the challenge in all this. For example, you have a task where you need to detect faint lights, yeah, and you have a sensation basically that is like in that range here. Then the next stage of processing that looks at the initial neuronal activation doesn't know, okay, it's a no signal, noise only situation, or it's a signal present but relatively low noise level situation. And the criterion that you put here, represented by the vertical line, tells you, okay, if I measure a value that's to the right of that cutoff line, then I simply declare it as signal is present, as light is present. And if it's to the left of this line, I simply declare it as no light is present. And the position of this line, I'm basically, as an observer, I'm basically free to put it wherever I like. Yeah, that's my decision as an observer to say, okay, this is my position of the line and it's not here or here. Of course, I'm usually not doing that consciously. I'm not, but maybe sometimes I'm thinking about it, oh, was it a light or not? And then maybe I'm choosing this consciously, but very often probably I'm just doing that unconsciously and saying, okay, I haven't seen anything, let's press the no button in that experiment, for example. And then we get to what's d prime. D prime is the distance between the two peaks, which represents the signal divided by the width of the peaks, which would be like this. And this basically tells you, this ratio tells you also how much they overlap, because if they are far apart, the two peaks here, and the mountains are very narrow, then there will be little overlap. And if they're close together and very broad, then there will be a lot of overlap. And that's what basically D prime tells us. D prime tells us how far are they apart in terms of their width, how many width, basically the width is taken as a measure of farness of apart. Basically it tells you, okay, there are 3 widths apart, or 10 widths apart, or just half a width apart, and half width apart is of course less good than 10 widths apart. So yeah, I went through all this, I think, more or less, so we can go there. And you can further describe that as what's called a receiver operating characteristic, and you might have seen such plots already in some scientific papers when you look at diagnostic procedures, for example, where you want to understand, or the authors have tried to convey the message of how well a diagnostic procedure can differentiate between, for example, a healthy case and a case that has a disease. There they make similar plots, and what it shows is basically here the false alarms in percent on this axis and the hits on this axis. Hits means the person has said, I see it, and it was really there. And of course this curve has to start up here, because if, it will become clear in a moment why it has to be up there. Because if we place this criterion line here to the very left, somewhere outside on the sea over there, basically, then you catch both hills completely. Yeah, they are both on the right side of your line when the line is way out there. Yeah? That means you have 100% hits because you catch this curve completely, but you also have 100% of false alarms. So whenever there's a light, you will say there's a light, but you will always say there's a light when there's no light. Easy task in that case, yeah, but that's the point up here. 100% false alarms, but 100% hits. 100% hits is good, 100% false alarms is bad. And if you move that line now a bit towards the right, let's say here, then you still have more or less all of this mountain that goes down here. You cannot really see it. And you have cut off a bit of this one. So a bit of this one's now to the left. So we have still almost 100% hits, but we have a bit less false alarms because we have cut off this triangle, basically. And we continue, move that line to the right, and again to the right, and to the right, and we walk along that graph as it's displayed up there. And then, in the end, we get to the point 0, 0. And 0, 0 is the point when this line has been moved very far to the right. Yeah? Then both of these are to the left of the curve. That means we have no false alarms because that complete curve is on the left, but also this complete curve is on the left. That means all the lights, so whatever the strength is, even if they are clearly visible, we say no, there is no light. Yeah, easy task, not very useful, but it would bring us to this curve, or this point here. And going through the criterion values basically results in this curve. And I've already mentioned that. Importantly, D prime, which was that how far these hills were apart in terms of their width, this is unrelated to the observer's criterion. But a large D prime means the curve goes into this corner here. And a small d prime means it's close to the diagonal. And if it's in the corner here, if it's going into the corner here, that means that there's a point on that curve that means few false alarms but a high hit rate. And this is something you can achieve with a large d prime because there's little overlap of the curves. And if you have a small d prime, that means the curve is near the diagonal. And then it's impossible to have both high hit rates and false alarms because the false alarms increase together with the hits, and yeah, they are always the same then. So different d prime values result in different ROC curves, and the observer's criterion basically gives you a point on the respective ROC curve. Yeah, I already mentioned that. Oh, yeah. And I already mentioned that this is very similar to the evaluation of diagnostic tests. The hits correspond to what you see plotted as sensitivity when you get such plots for diagnostic tests. And the percent false alarms is often, which is down here, is then plotted as 1 minus specificity, and d prime corresponds to a measure that's known as Cohen's d. And now it becomes more and more interesting actually for your acuity tests. Yeah, we are slowly getting there, but we needed basically start slowly and a bit complicated, but we are getting there. We can take a different perspective on signal detection theory. So the signal might be present or absent, and then we have that sensation, which is the initial neuronal activity that the stimulus creates, and there's noise in the system, yeah, which means that the sensation is not always exactly the same, because basically the sensation is the noise in that moment plus the signal is coming from the outside. Then you have here the sensation level, basically the output of the sensation stage, and then you have a decision stage, which kind of looks at the sensation stage and says, okay, with that sensation, I decide for present of the light or absent of the light. This is basically what we have gone through already. And this requires a criterion which says, okay, this is my cutoff for the decision. And then you say either yes or no. This is all nice. The problem is you cannot get rid of the noise, but you can see here, sensation and decision can be considered separately. It's an abstract level. It's not meant that this is exactly how it is implemented in the brain, that there's a single decision stage and a single sensation stage, but it's basically a model that helps you developing the theory. And as we have seen, without noise, a perfect detection would be possible. Then basically you have these, then you can place the criterion in the middle of the signal absent and signal present situation. You don't have these mountains here, everything is nice. And then you get 100% in this corner of the table, 100% down there, everything wonderful. If there's noise symbolized here through these, or by these mountains, then it's getting more challenging, and we have gone through this, but we could change our question now, and that is something that might help if we just change how we are asking our patients. And of course we have to adjust maybe the presentation of the stimuli so that we can ask a different question. And we could ask now whether, no, not whether there's a stimulus, but we could ask what stimulus is there. And maybe you're already feeling that we're getting closer to acuity testing, where you're also not asking, is there something on the chart, but you're asking, what is on the chart? And yeah, that's the graph that we just had, and we can branch off here. We leave this part out, we simply take it basically a turn off here, yeah, and we have the different task. The different task would be to ask what is there, and this then the response could either be correct, that the person gave you the correct answer, or it could be incorrect. For example, the person read the correct letter on the acuity chart, or it was not the correct letter. And this is called forced choice, because the person has to tell you the letter that he thinks it is. Yeah? The patient is not allowed to say, oh, I cannot really see it, let's skip this, or let's stop here. But you are forcing the patient to say, okay, this is whatever letter. And that's good for vision testing, because you get rid of that criterion. Otherwise, it would depend on the character of the patient, of the personality, where the person would say, oh, I can still see it, because it's a person who's very ambitious maybe, and always want to achieve something, and so on. The person would really try very hard, and whatever is there, the person would say, oh yeah, it's there, because he always wants to be the best or so, yeah. And other people, maybe they for sure don't want to do anything wrong, and for them that means, if I'm not completely sure, I rather say it's not there, yeah. And that's something you avoid when you're doing when you're asking not is it there, but rather what is there. And therefore, it's good for vision testing. Yeah, that's what we already said. And yeah, an example of a psychophysical test is acuity testing. The international standard prescribes the Leinol-C, but you can also use others. Many of them, especially the tumbling E, give roughly the same results. But in these, the question is not is there letter, but rather which letter is it. And so I like using the Leinol-C. It's an 8 alternative forced choice task, because it could have 8 different orientations, as you all know. And the patient responds correctly with a certain probability. And acuity testing is, in that sense, to some degree, a random process. And that becomes maybe, and the probability depends on the size of the optotype. And why it's a random process, to some degree at least, of course not completely, if it would be completely random, the test would be useful, and not useful, but to some degree it's a random process described by the psychometric function here, and that looks very similar to what we had seen in the very beginning. And here you have small optotypes, here you have large optotypes, you have the percent of correct answers, of correct responses. And if the optotypes are very large, then you will always get correct responses. I mean, patients might make mistakes, but generally speaking, they are correct. Here, you're not ending at 0, like in the detection tasks, but you are ending at some value, which in the case of the Leinol-C optotypes would be 12.5%, because there are 8 different possibilities of what the response could be. And if it's so small that the patient really cannot see it anymore, then in 1/8 of the cases, the patient would still coincidentally give the correct response. Yeah? Therefore, the curve is ending at 1/8, which would be 12.5%. But otherwise, the curve is looking very much like the curve that we had seen already. The question is again, which point on the curve should be taken as an acuity value. And of course, again, it's the steepest point here, the inflection point, which is in this case the middle between this guessing rate here and the 100%. That's 56.25%. Then we go there, turn down, and read the acuity value, which happens to be 0 log mar in this example, which is in decimal acuity 1.0, which would be 66. And if that curve would shift for a patient leftwards, for example, after treatment or so, or with better glasses, that would mean better vision. And if that curve would shift rightwards with the next visit. Yeah, that would mean maybe the impairment has become worse. There's maybe a progressing disease. And this is, of course, a theoretical curve. An acuity chart usually has a cutoff criterion when you stop testing. So the criterion could be, for example, 3 out of 5 should be seen, or 6 out of 10 should be seen correctly. But that also ends up roughly at that same value, not exactly, but roughly. And interestingly, that end here of that line where I said, okay, it's 12.25% because of the 8 orientations of Lennard Z, that's quite undefined in case of letter charts, because letter charts do not use all the letters that are available, not all the 26 letters, but the patient probably doesn't know about that. So in theory, you could say, okay, there are, I don't know how many, let's say 10 different letters or so, though it would be 1/10. But the patient maybe thinks, okay, he has to choose from 26 letters. It might give responses that are impossible because the letters don't exist on the chart. So this end of the line is actually kind of undefined with letter charts. Yeah, so we have gone through signal detection theory quite a bit. Could this be applied to a Lennard Z as well? Yes, of course. And we could describe it as here, where the gap is, we have signal and noise. Yeah, the gap is actually this kind of our signal that has to be detected to know what the orientation is. At all the other possible orientations or other possible gap locations, we have noise only because the gap is not there. And now the question is, the next stage, this perception stage of the process, yeah, or what does that stage see? And we have 7 options with noise and 1 option with signal and noise. And you can now imagine if that signal is relatively small, and this point here has its kind of its personal noise value. Yeah, if that noise value also happens to be small, but maybe down here there happens to be a lot of noise, then this value here might win over this value here. And then if the next stage that doesn't see that Lennard Z by itself, but just has to rely on what it is told by the preceding stage, thinks, okay, this is the largest value coming from down here, so the gap must be down here. And that's even if it's wrong, because it's just a relatively small signal and a small amount of noise. And you can imagine that if we have 7 possibilities of noise, it's actually quite likely, if the signal is small, that one of the 7 possibilities will win over this value here. And that can be described mathematically by this equation, which you don't need to write down. I just want to say it can be described. Interestingly, in reality, this theory is not true, because if you test it in Lennard Z, the gap positions are not confused with equal likelihood. If the gap is here, people tend to say it's here more often than that they say it's here when they are giving wrong responses. So the neighboring directions, near the threshold, the neighboring directions are chosen more frequently. So to summarize, that decisions have to be based on noisy sensations, because that's all that's there. Decisions are reached by applying a decision criterion. The choice of the optimal criterion depends on costs and benefits. And sensitivity, D prime, has nothing to do with the criterion. And large D prime allows for high hit rate with few false alarms, and forced choice tasks are independent of a criterion, because you remember we turned away from the usual way of processing and asked a different question. And there's one thing that we haven't considered yet, which is the base rate. And I want to illustrate that with a base rate fallacy. Imagine there was a murder somewhere, and the police is asking the witnesses what happened and so on, and the witness said, "Oh, I've seen the murderer, he fled in a blue taxi." Yeah? And of course the police wants to find the murderer, and the police knows witnesses are right in 80% of the cases. So should they search for a blue taxi or not? Sorry? It depends on the data. And what kind of data would they need? Yeah, so it's maybe worth focusing on the blue cab taxis first, or if they have limited resources. Well, I want to make the point that it depends on the data, but on additional data. Imagine you have 1,000 taxi cabs, yeah? And there are 850 green ones and 150 blue ones. So there are many more green ones. And if the witness is in 80% of the cases correct, then of these green ones, 680 would be seen as green, but and 170 would be seen as blue. And from the 150 blue ones, 120 would be seen as blue and 30 would be seen as green. So if you look at these two numbers, 170 and 120, then there are more green taxis that were seen as blue than there were blue taxis, really blue taxis that were seen as blue. So if the police knows that there are many green taxis, then it's rather worth looking for any taxi, yeah, probably, than focusing on the blue taxis, because the likelihood for finding the murderer in the green taxi is actually higher than finding him in the blue taxi. And that tells you it depends. I mean, if you know that you have like a weird acuity chart that where like almost all the letters are, let's say, K's, yeah, then if you are not sure what you're seeing, maybe you should rather decide for K to be correct, yeah, if you know that. And that's basic additional knowledge you need to put in, if you know it, to improve your decision. So that's called the prevalence, and the prevalence is something you might have heard already also in diagnostic situations. If something has a high prevalence, then it's very likely that such a patient comes to your office, and if the prevalence is low, then it's very unlikely, and so that it also has diagnostic consequences. And then there's a branch of statistics called Bayesian statistics that can be that basically accounts for all these things, and which can be combined with signal detection theory already also. And the brain very often does this automatically. For example, in context-dependent recognition of people. Imagine you're back home, at the home of where your parents are living, and you're not really paying attention to what's going on, and like you're seeing somewhere a woman walking, yeah. If it's in your parents' home, you will immediately know, okay, this is my mother, yeah, because it's very unlikely that there's someone else looking like a woman and your mother. If you're walking here across the campus, seeing someone who gives you the same visual impression, yeah, your first thought will not be, oh, this is my mother, but rather maybe this is the professor that I have in that other class that is also female, maybe looks remotely like my mother, yeah. Could be that professor, yeah. So the brain is automatically kind of pre-processing things, so it presents you already with a likely solution, yeah. And sometimes it might be wrong. I mean, it could happen that your mother is coming because she thinks, oh, you have forgotten something important, and she wants to bring it to you, yeah. Unlikely, but could be possible. And then your brain would be wrong in telling you it's that professor. what is this, what you are seeing there? And now I think the projector is doing a good enough job to present it. One is raising the hand? Exactly, that's what it looks like to most people, at least. And the question is, has everyone this impression? And the question is, why is this impression? Because I mean, it's a flat screen, yeah. There's no third dimension that it protrudes out, or nothing goes in kind of behind the screen or so, yeah. Why do we see it as something three-dimensional? And there are two things playing a role here. One is what's called shape from shading, that different gray levels tell you something. And more importantly, in this case, there's what's called the light from above prior, which is the visual system is kind of trained to assume that light is usually coming from above, because the sun on average shines from above. It's usually not coming from the ground, yeah. And also, even in modern times, when you have room lighting, usually you have some light at the ceiling, and normally not coming from the ground. There are exceptions to that, of course, yeah. And you can see that there are these edges that are a little brighter and these edges that are a little darker. And these cause the brain to use this assumption here, that light from above prior, to transform this into a 3D percept. So this is something that's continuously going on, that the brain uses experiences, assumptions about the environment and so on to pre-process what it is presenting to your consciousness. And you can imagine that's actually quite a challenging task sometimes. And also, I mean, even if you see something real that is in reality a 3D object, later when the image of it hits the retina is a 2D surface, yeah? So whatever you see has gone through this transformation that it's just 2D. But the brain needs to create a 3D percept to help you understand how the things look like. So this is something that the brain is constantly doing. And that, of course, can also create nice effects like this one, where depending, I mean, this is obviously in the sand down on the beach, yeah, not something vertical, but nevertheless, depending on from which side you look at it, it might look one way or the other. So what is this? I would say a square, yes. Anyone disagrees? Well, a square is a good guess. But in reality it's this, which is something that most people would perceive as a 3D object, basically a wireframe of a cube. And we have the idea, or our brain has the idea, that cubes look like this. And if you look at it exactly from the front, from sufficient distance so that we don't get any perspective problems, if you just see this, and especially when it's on a screen like here, then we don't perceive it as a cube, because this is basically the generic way of how we expect a cube to look like, and this is not the generic version of a cube, how it looks like. So we have, again, certain assumptions on how things look like. That's called the generic viewpoint assumption. This is a nice example also. little video that hopefully works. Yeah. You see that elephant, and the guy is now turning this, and it transformed into different animals. And it can be reverted, and now it's back to being an elephant. So this does not only work on a computer, but also in reality. And this is something you can make up your mind what it is. If you know what it is, don't tell it. And I will now show the video. So sometimes we are misled into thinking that something is different from what it actually is. And of course here also the orientation was not the usual most expected one, yeah. And then we were misled a bit. And this is also a kind of well-known figure in vision science. I don't know what you are seeing here. You're seeing a rabbit or a duck, yeah. That's the rabbit and duck image. And someone actually has done a study, and has done a study two different times of the year. That was, one was around Easter time and one was in October. You asked children below 10 and above 10, I don't know whether they were adults as well, probably. And around Easter time, most of them said it's a bunny or something like this. Animals looking similar to a bunny, and like, yeah. And here in October, they mostly called it with some bird names like a duck, a stork, a flamingo, or whatever. Or they just called it a bird. And this seems to be a kind of a contextual effect. And for that, you need to know that, at least in like German tradition, I think that was actually done in Switzerland in front of the zoo in Zurich, but they probably have the same traditions as the Germans. Around Easter time, people expect Easter bunnies to bring little gifts, hide them somewhere, and the children can then search them. So the mind is maybe preset to see bunnies, yeah. And that's not the case in October. Maybe this is more like birds flying around, and yeah, from Central Europe, the birds start migrating to Africa maybe because they don't like staying in the winter in Europe, yeah. So maybe people see more birds, and then I don't know why exactly, but there seems to be like a temporal context effect. So context matters in vision. What do you see here? 3 different shapes, exactly. And what is, yeah, it's not yet there. What is this? Let's create, what is this? Maybe, yeah, maybe a circle made up from these little segments. What is this? Yeah, it could be a triangle made from like four different bars or something. So this is a bit weird. I don't know what it could be. Looks like inverted stairs, exactly. Then we have this one. Castle maybe, this one, well. And then we have this one, and I don't know whether you have now, and it's an S. And then maybe you can guess that if this is an S, these are also supposed to be letters. It's a bit difficult to read still if you don't have the local context, but you can already guess that it's letters. And that's the San Francisco Museum of Modern Art, which had this logo in the 1990s. So context matters. If you're living in San Francisco, you know that it abbreviates itself as SF MoMA, then you might guess that immediately. Here you start guessing it's letters, but you're missing maybe a bit of the local context. But now, again, what is this? It's still a bit challenging, but from the context that I'm asking you again, you might guess, okay, maybe this is also letters. And now we have this, it tells you even more that it's letters. What? Loca? Mocha? Yeah, so it's MoCA, M-O-C-A. And this is also a museum. This is the Museum of Contemporary Art in Los Angeles. So context matters. You could guess that these shapes are letters after I have presented you that other one, and I'm asking again, so maybe, okay, letters this time. We were not fully sure because you didn't have maybe that local context of Los Angeles. So context matters a lot. Now the question is, how are we in time? No one wants to give me an official read of the clock, or give me an official allowance. Yes? 35 minutes? Yeah, more. For the first 2 hours or 2 lectures? Yes. So I'm still in the second slot. Okay, I thought I would have used up much more. Anyways. After that fun part in between, where we looked at context effects of perception, we are getting back to something that's more theoretical, but I hope you're a bit refreshed now. We are now looking at Bayesian statistics, and I'd already mentioned Bayesian statistics when I talked about this murderer who fled in a taxi. Yeah? There I said at the end, okay, this could be described with Bayesian statistics, and now we try to get to that point. And the reason, let's say not the reason. And I'm using an example from the external world, which can be easily described because it's sometimes a bit tricky to describe what's going on exactly in the brain. But I'm using an example in the real world to illustrate something that we assume is going on in a similar way also in the brain. Yeah? Basically, the brain has to detect things, and I'm now showing an example where in real world there's a detection task, and I'm showing what the challenges are and the contributions to the outcome. And you could think of this as a kind of a model of what's going on in the brain. And so the example is there are fruits entering a warehouse on a conveyor belt. And someone is sitting there and deciding, or has to decide whether it's an apple or an orange. And this might be an important task because they have to be stored in different rooms in the warehouse because maybe the apples like it colder than the oranges, or the oranges like some other environment with a certain atmosphere, or I don't know. Anyways, they don't like to be in the same storage room. And if you want to do that mathematically, we could say, okay, W is the type of the fruit, so we have W1 is an apple, W2 is an orange. So far so good, that's simple. Then Bayesian statistics is all about probabilities. So we say, okay, the probability that we have an apple could be described as P of W1, because W1 was the apple. And that specific probability here without any further indication. Just W1 in here is a prior probability that the next fruit is an apple. Prior probability means that's the assumption you have about that fruit without knowing anything specifically. You haven't actually examined that fruit. You have just a priori assumption about what's coming in. Yeah, and that's the a priori assumption that you have. That's is given by that probability. And you have the same for the oranges. And if you have no clue whether it's more likely to get apples or oranges, then you simply assume that both are the same. And if you have just two, then clearly both of them need to be 50% probability. And now you can develop decision rules, because you have to decide which fruit is it. And you can, altogether, there are different decision rules. One could be based simply on prior probabilities, that these were these p-values that we just saw. Then you could decide based on posterior probabilities. Let's see, oh yeah. Prior probabilities were when you are not collecting information about the individual objects. That's related to what we have already seen as prevalence. So the posterior probabilities use information about the individual object. So the object needs to be examined somehow, and then you know more about the object. And this will, of course, help you deciding. And then you could decide based on risk. And that accounts for the consequences of the decision. It's a bit like the child that thinks, okay, monsters are very risky, so I rather tune my decision to make sure that I won't miss any monster. Yeah, that's basically a decision that also incorporates the risks. In this case, an assumed risk that, that's what the child thinks about monsters. So, if we are using just priors, we just use that a priori probability what probabilities the fruits have when they come in, without looking at them really. And then decision is very easy if you want to perform good. You simply know, okay, one of them has the higher probability, then I always decide for the one with the higher probability. If I assume, okay, there are like 70% apples and 30% oranges, then I rather classify everything as an apple, and then that's a good strategy. That's what this equation says. If apples are more likely than oranges, then I will decide for apples. And if it happens to be the other way around, then I decide otherwise. But it will always be the same decision, because I don't look at the fruit. I just say, okay, apples are more likely, then let's say it's an apple. Of course, I'm making mistakes. The mistakes correspond to the likelihood of oranges, because whenever an orange comes, I'm making a mistake. So the orange probability gives you the probability of making a mistake. Then I start examining the fruit. I have a measurement device, and I try to measure the lightness of the fruit, for example. And that could be called X, and I'm trying to improve my decision using that lightness value. The good thing is Bayes tells us how to combine the a priori probability with a new probability that I'm getting from this measurement. But of course, I need to know something in addition. Because if I'm getting a certain lightness value, I have to know what does it tell me about the fruit. And it will tell me with a certain lightness value, it's pretty likely that it's an apple and not so likely that it's an orange. But usually it won't give you 100% certainty. And the other value will give you different probabilities, but again, not 100% certainty. And this will be, then these certainties or probabilities are called the class conditional probabilities. That's the probability that that you measure a certain lightness value when you have an apple, and the probability that you measure that lightness value when you have an orange. These are probabilities that you need to know, and this can be plotted, of course. These are the lightness values, these are the probabilities, and oranges and apples have their different lightness distributions. They overlap usually, and that's a picture that we have already seen before. Yeah, it very much reminds us of what we have seen very originally with this no stimulus, and we could also use this not for no stimulus, but for apples versus oranges. Yeah, apples have the maximum here on that scale, and oranges here, but in fact the measurements will scatter around this typical value. And then there's Bayes' rules that tells us how to combine them. And basically that says the probability that an object is an apple is high if the measured lightness is typical for apples and it's probable at all that it is an apple. I mean, if there are no apples coming, it can be as typical as it wants to be as, with lightness. Yeah, it cannot be an apple, even if the lightness is very typical for an apple. And if there are very, very many apples, like 100% apples, let's say, then whatever I measure, I don't need to care. Basically, it will always be an apple, and the truth is somewhere in between. And that's basically the main explanation of that equation. And then you get a new probability, and again you decide for the probability that now incorporates both that lightness value and the a priori probability, and you take the one that tells us the probability of the apples, and if that's bigger than the probability for the oranges, then you decide for an apple, and if it's not, then you decide otherwise. And you get, again, of course, get an error. The error will depend on what's less likely, because the one that gets the less likely probability will always be the one that gets the error. And these probabilities will look like this, and we can place a decision criterion here in between, and then we can decide. And that's the case for equal a priori probabilities, and that shifts then, for example, to the right if we have an a priori probability in favor of, let's say, oranges. But I think the graphs per se are not that important. The important thing is to see that we have a link between the a priori probability that tells us what's coming in with what probability, and the probabilities that the measurement tell us, and we can combine that to an overall probability. And that can be used for decision. And the brain does that all the time. It collects information. Yeah, it's basically like measuring the apples and oranges. It has an a priori assumption what the likelihood is of certain things happening, that light is coming from above, or that the grandmother is not walking around on campus, or all these things, yeah. And then we can introduce risk. This can also be described theoretically. The main thing here is, I think, to see that risks can be included in this computation. And all these decisions are completely meaningless if they don't result in an action that you are taking. Yeah, you can find out exactly that it's an apple or an orange, even if you would be 100% sure. If you wouldn't actually start sorting the apples into their respective rooms, you wouldn't have to decide about it. Yeah, and if you don't sort them into rooms, you're also not really making a severe mistake. I mean, it's nice to call an apple, an orange, but if you call an apple an orange, then no one would care, unless you really use that information to do something seriously wrong. Yeah, and therefore, all these things need to incorporate the risk somehow. Yeah. And that's also partly what the brain is doing, that it's not bothering you with everything that's going on around you. So if you are walking through the street, not every noise will distract you. But maybe if you're hearing a car coming there and then you hear like the noise as if it was braking hard and maybe cannot turn around the curve, and then your hearing sense or the hearing system will alert you that you should turn around, check what the car is doing. Maybe you have to jump to the side and make sure that you're not run over by the car. Yeah, but if it's just something else, if it's loud aircraft passing, then you would probably not care. Yeah, because you know that the aircraft won't hit you in the street. Yeah, and therefore the brain will pre-process things for you and alert you primarily of things that are relevant for you. And that's important to understand. And that is also a bit related then to these types of attention that I had mentioned, was it yesterday or the day before yesterday? These different types of attention, that there are types of attention that are linked to certain features, certain properties of things, certain characteristics, and you are basically looking out for something. And to some degree, the brain is automatically looking out for things that might be relevant for you. And you can, of course, consciously change that to some degree by basically giving your brain a task to do. And then the brain maybe will also look out for something specific. And if you're basically expecting to meet your friend somewhere, then you will look out for your friend and spot your friend. And if you're not expecting to meet him somewhere, maybe you will miss him passing by. And yeah, all this again has to do with its monsters. And let's skip this. And let's get to the last slide, actually. So we have learned today what is psychophysics. Basically, there is that inner psychophysics that we are usually not thinking about when you're talking about psychophysics, but it's important in the theoretical sense because it's linking physiology with the mind. And even if we don't think mind and physiology are completely different things, it helps thinking about these things from a theoretical perspective. And we have continued to talk about thresholds, about the Weber-Fechner law, about signal detection theory, criterion, sensitivity, and so on. That was a bit theoretical. We had found out that forced choice is actually a good thing to do, and luckily vision charts have in principle provide us with this option. We just need to give the correct task to our patients. We had quickly a look at the base rate fallacy. Then here, not shown here, we had a little intermission with a few things that were more relaxing but also meaningful in this context. And then we continued with Bayes, which was a bit tougher again. And I think the main thing is here to not all the equations, but understanding that we basically there are a priori assumptions on how the world is, and then the stimuli help us to create a posteriori probabilities of what we see here, so that we know, okay, we know that something could be, and the stimulus says us, oh, it's really very likely this. And then we also risks and losses are taken into account. And overall, the visual system tries to make sense of the input, and that's a big challenge for the visual system, because what the visual system gets as an input is a 2D image, and parts of things are hidden by other parts, for example, and certain things are not seen very clearly, maybe because we see them in the periphery, and we nevertheless they might be relevant for us. So the visual system is constantly working on making sense of the input, and overall it's doing a pretty good job, even though sometimes, of course, it's not doing exactly what we are hoping for. And one thing I would like to invite you to do is also to look at visual illusions, like on the webpage of Michael Bach, who was formerly my supervisor and then my boss, and now he has retired. He has collected, I don't know, more than 100 visual illusions on his webpage, and which you can access, I think, through michaelbach.de. And then there's a Michael Bach in one word. There's a link to the illusions. And many of the illusions are actually not things where the visual system really fails in a bad sense. But the visual system is basically tuned to our normal environment. And in the normal environment, certain things make sense. And of course, if you tweak stimuli in a way that they are simply not what you encounter in the normal environment, then the visual system might present you with something that's not really there. But in a sense, it's the result of an optimization of the visual system and not so much a failure. And yeah, I know that a few things were a bit theoretical, but I think even if you haven't understood every little detail, some people are more scared by equations, others not. I've skipped a few. Just having the idea of these things, like the concepts, I think is a thing that can help understanding what's going on in these tests. And even if you don't recall every little detail that I mentioned, maybe you remember some faint idea of what I told. And then at least you know that if eventually you run into problems with something, or you think you have to design a new test because what's on the market is bad, then you can do that with some prior knowledge already. And that was the idea of this lecture. And now, of course, I hope we have still time for a couple of questions.
Yeah, so we open the floor for questions.
Yeah, one person is raising the hand.
Thank you, sir, for the educative presentation and lecture. So my question is, I'll use it both on the subjective aspect and the objective tests. Where an observer, let's say a practitioner, observing the optic disc, and let's say 4 different observers. A, let's say, assuming the threshold is of normal is 0.5 copy, this copy, and A said he records 0.5 and he said it's glaucomatous, and B says 0.5 and he said this patient is normal, and C says record it as 0.4 and he said normal, and the last one says 0.6 and he says it's glaucomatous. On the psychophysics, which is, because it's a missed target and we have both miss and hit, which is advisable considering the patient health and the danger of glaucoma to the patient? Which level is advisable to stand on based on psychophysics? Then on objective, we have taken the intraocular pressure instrument to test, and the number that is considered the threshold says is 21 millimeter mercury, and instrument A is measuring 22 millimeter mercury. Meanwhile, if this patient is actually have intraocular pressure that is high, but instrument B is measuring as 20 millimeter mercury, there is a false positive and there is a false, there is a true positive and there is a false negative. So which instrument, or what is the stand of psychophysics when we have such two scenarios?
Yeah, I think the first thing to recognize is that every measurement has a distribution of errors, and also what's considered the cutoff value for a decision. Yeah, it's also based in the end on a probability distribution. I mean, at some point, some committee said, okay, the cutoff is this value, but in fact, this is not a value where you can say, okay, if it's below, it's for sure healthy, for example, and if it's above, it's for sure disease. Yeah, but there will be people with a lower value that have a disease and people with a higher value that have no disease. So in the end, there's no absolute yes, no answer to all of these things. And that's kind of goes through all that chain, yeah, and that's a big problem in all this. And very often, I mean, even in those cases where you don't have a single value, but something like a reference range, yeah, you have a reference range that's defined by, let's say, 59% of the so-called normal population, yeah. If you get something that's outside of the normal range, it could be one of the out of 20 normals that is normal, yeah. And you maybe start treating the person with something, tell the person, okay, you have to take this medication, maybe the medication has side effects, or whatever, yeah. But the question is, could you do better? And that's not always easy, because maybe, well, you can say, okay, the value is out of the normal range, so at least from a kind of a legal perspective, I say, okay, I can have to classify the person as having that disease, yeah, but nevertheless, he might be healthy, yeah. And the only solution that I have is to collect more evidence. Maybe, I mean, one thing is, of course, you could repeat the measurement and see whether there are some random fluctuations in the measurement. That would be one possibility, or collect other evidence, maybe do a completely different test. And to some degree, you do that in glaucoma, that you measure the intraocular pressure, you look at the cup-disc ratio, you maybe do other things. Yeah, I'm not a clinician, so I don't have any advice as to specific tests, but probably you could do other tests, and sometimes it's just your feeling that this doesn't look normal, yeah, maybe. And this feeling, of course, relates to something. It doesn't come from nowhere, but it's difficult to pinpoint what exactly causes that feeling. But nevertheless, that's also a component. If everything is borderline, basically, and then you add in your feeling, then maybe it's justified to also say, okay, my feeling has a value, yeah. And so it's challenging, and there's no simple answer to that, and any robust answer would also need to take into account, and now I'm already talking since a while, yeah, but it's a complicated question. You know, for example, the distribution among healthy people, but you usually don't know the distribution among people with disease in many cases, yeah. And the disease is not just the one state of the disease. Most diseases start slowly, yeah. So whatever disease there is, on the first day when the disease starts, let's say, it's still, in most cases, fully in the normal range, yeah. And only when the disease progresses, at some point, it will possibly leave the normal range, and then you might say, okay, the disease is there based on that normal range. But in reality, it has already been there since maybe 3 years. You just didn't accept it as disease because it was still normal. So the whole topic is quite complicated, and there is no simple solution to that, except saying, okay, is there a possibility to do another test that tells me more? And then to decide, okay, what's the risk and what's the benefits of a treatment? Yeah, and maybe there are easy treatments for certain conditions where you could say, okay, I'm not fully sure, but let's do that. Because if I miss that disease, maybe it's some, let's say some germ that infects the eye, yeah? And you are not sure, is there an infection really or not? You might want to, or is that that specific extremely aggressive germ, yeah? But you don't know it. And you don't have laboratory results yet, yeah? Maybe in some case you want to give an antibiotic just to be sure, if you think it's a bacteria, yeah, that you fight against it, because you know if you miss that in the early stages, it will become a really big problem, yeah? But you give that because of an assessment of risks and benefits, and you think, okay, the side effects are not that big, but if it's that germ, that bacteria, then the benefits are huge that I start early. And so the decision is pretty complicated, and it relies on basically your experience as a professional, what you have been trained, what you have seen over the years of professional experience, of what you can read in the textbooks, and in the end there are cases where you just don't know, I guess. Long answer for, in principle, a simple question.
Thank you very much. This has been a very interesting lecture. I just want you to please throw a little more light on the false choice versus detection. Maybe after that explanation, if I'm not very clear, I'll ask a question.
Should I go back?
Yes, the portion about the false choice versus detection.
I need, where is the there it is, yeah. You say stop. Was a long presentation. We go through all the nice things here. Okay. I think now we are beyond forced choice already. In which direction should I?
Forward.
Forward.
Yeah. So, yes, if you could just explain a bit. Something that's not really clear.
Okay, so there's a concept or this model of how things work in perception, that we have the first stage which converts the incoming stimulus into neuronal activity. And then there's a second stage that needs to decide on it. It doesn't watch the stimulus directly, but it looks at the preceding stage, which is the neuronal activity that was triggered by the stimulus. And that stage, based on neuronal activity, has to decide, for example, is there a stimulus or not? And the neuronal activity basically could tell something which is not the truth, to put it simple. Yeah? If the neuronal activity that fluctuates all the time, sometimes it's a bit stronger, sometimes a bit weaker, and if it happens to be strong in that moment when the decision needs to be achieved, then the decision stage will say, oh, the neuronal activity in the sensation stage is so strong, there must be a stimulus, even though it was just a random fluctuation in that moment. And the other way could be that, well, the decision stage knows what the average level of neuronal activity is, of course. But when the fluctuations are very low at that moment, then a weak stimulus is not enough to bring that activation level to a level where the decision stage would say, oh, that's an activation level of the sensation stage where I think I should decide for yes. So basically you are adding up noise which could be low or high, and a more or less weak signal. And if the the weak signal plus weak stimulus, weak noise, doesn't give a weak neuronal activity, that would be classified as there's a stimulus. And the other way around, strong neuronal activity because of these fluctuations could be sufficient for the decision stage to say, oh, it's so strong, there must be a stimulus, even though no stimulus was there. And that's the idea behind it, that there's noise in the system, and that noise makes it difficult for the decision stage to always reach the correct decision. I don't know whether this has helped.
All right, thank you very much. We'll break at this stage for snacks. If you have any other questions, you can speak to
But I should alert you, I have to rest my voice a bit now, because I will have to do the next 2 lectures as well. So maybe we postpone difficult questions to the afternoon, maybe.
The usuals for snacks.